Hello seniors, hope you guys are hanging in there. We are week 3, distance learning. Isn't this exciting? I miss seeing you, I miss laughing with you, I miss all of those jokes. We're doing some new stuff today. Hope you guys are doing all right. We are talking normal distributions today. So this is new stuff for us. We're going to do this week and a little bit of next week before we move on. So normal distributions, I am not making this up. It is called the 68, 95, 99.7 rule. As always, boy Reginald's going to help us out. Again, 68, 95, 99.7. I'm going to keep saying that, and we're talking normal distributions. Normal distributions, they are symmetric, single peak, and bell-shaped. They look like this. If you're drawing a normal curve, it looks like this. I might have said in the past, describe the distribution, the shape of it. This would be symmetric or single peaked or bell shaped. That's a normal curve. Sometimes they are tall and skinny. And sometimes they are short and wide, but those are all normal curves. Things that are normally distributed would be things like intelligence. Most of us are right around the middle. The vast majority of us are just a little bit above or a little bit below. Some of us are way above or way below. Other things that are normally distributed, things that you measure in nature, height, weight, length, things like that. Our weight is normally distributed. Most of us weigh just about this much, and then the distribution thins out as you go towards the tails. Let's see, whenever I write something that's normally distributed, I write capital N for normally distributed. Let me scoot that over. Capital N for normally distributed, described by the mean and standard deviation. Okay, here's a normal curve, something that's normally distributed. This is the standard normal curve. So this is when it has a mean of 0, and then it goes up 1, 2, and 3 standard deviations above the mean, 1, 2, and 3 standard deviations below the mean. This is the standard normal curve. So usually this one standard deviation away from the mean is right there. And we've done standard deviation a little bit before, that z-score. That's how many standardized values. Standard deviation is the typical amount that it deviates from the mean or the center. All right, here it is, brand new info, 68, 95, 99.7. So I've got 3 regions here. This is that standard normal curve. This right here is the mean or the average. And then it's 1, 2, and 3 standard deviations above the mean, 1, 2, and 3 standard deviations below the mean. So see these 3 colors here? I've got, what would we call this? Maybe a mint green. We're going to call this one the sage green, and this one the olive green. Okay, so 68% of all observations, 68% of everybody is going to be in the mint green area. 68% are within 1 standard deviation of the mean. See this notation right here? The mean is mu and the standard deviation is sigma. Mean is mu, standard deviation is sigma. We've seen that before. So 68% of everybody is in the mint green area. See how it's almost everybody? It's more than half of all of this. More than half of all of that is in the mint green area. Let's change that color. Okay, and then that's 68% from here to here. 95% are from here to here. 95% are in the mint green and the sage. So almost everybody is in that part right here. 95% of everybody is there. And then the third one, 99.7% of all observations are within 3 standard deviations of the mean. So I've got 68% in just that mint green area, 95% in the bigger area, and 99.7% in the whole thing within 3 standard deviations above the mean. Here's another picture saying the exact same thing. Let's see here. I've got 68% in the hot pink area. See how it's a total of 68% from here to here? If 68% is from here to here and it's symmetrical, then I would have 34% on the right and 34% on the left. Same thing if I've got 95% within 2 standard deviations. All of that's 95%. So that means I would have 34% here, 13.5 here, because 13.5 plus 34 plus 34 plus 13.5 is going to be 95%. 99.7%, that's almost everybody. It's 3 standard deviations from the mean. This one goes a little longer. So that's all the way down here. 1, 2, 3, all the way out there. 99.7%. So you can divide it up. This number plus 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 this number is 99.7%. If 99.7% is in the middle, is in this part, then I'm left with 0.3% in the 2 tails. We're going to have to play around with this a little bit more. But these 2 charts, very, very helpful. Okay, let's try one. The heights of palm trees at a local palm tree shop are said to follow a normal model with a mean 12 and a standard deviation 2. As soon as I read where it says mean 12, standard deviation 2, it's a normal model, mean 12, standard deviation 2. I always write that. Normal, mean, standard deviation. That way I can stop reading the problem. Draw a model for the palm tree height and clearly label it. So the mean is 12. That number right there in the middle is 12. The standard deviation is 2, so I'm going to do 12 plus 2 plus 2 plus 2, and 12 minus 2 minus 2 minus 2. Okay, number 1, done. Drew a model for the palm tree height. So this is the distribution of palm trees. The vast majority of palm trees are going to be about 12 meters tall. 68% of them are going to be between 10 and 14 meters tall. 95% of them between 8 and 16 meters tall. That's the idea. And so it's 1, 2, and 3 standard deviations above the mean, 1, 2, and 3 standard deviations below the mean. Okay, let's keep moving. How tall do you predict the middle 99.7% of palm trees to be? Let me just fill this out a little bit more. From here to here is 68%, between 10 and 14. 95% of all palm trees are going to be within 2 standard deviations of the mean. 95% of all palm trees are within 8 and 16 meters tall. 99.7 palm trees, that's almost every single palm tree, is going to be within 3 standard deviations of the mean. 99.7% of palm trees are going to be between 6 and 18 meters tall. How tall do I predict them to be? Between 6 and 18 meters tall. Okay, about what percent of palm trees are less than 10 meters? About what percent of palm trees are less than 10 meters? I'm going to do this in this little light blue. What percent of palm trees are less than 10 meters? That's this part right here. What percentage is that? I can do that a couple different ways. First of all, I can use my eyes to estimate. That is less than half. It's definitely less than half. The other thing I can do is I can use these charts up here. It's 1 standard deviation below the mean. I could add up those 3 numbers right here, 13.5, 2.35%, and that's up 0.15%. The answer is 16. What percent? 16%. My favorite way of doing that is this. If the middle is 68%, then that means in these 2 tails, I've got 100% minus 68%, I've got 32%. So in this tail right here, I've got 16%. There's 16% in this tail. The middle is 68, the tails are 32. 32 divided by 2, because it's symmetrical, is 16%. This is not easy stuff. There'll be another video to follow up with it, and we'll walk you through it as best we can. Okay. Number 4, about what percent of the trees are taller than 16%? So that means I'm dealing with this part right here, this area. If I'm looking at it and that curve, the area under the whole curve is 100%. Even if I were to just estimate this as a percentage, if the whole thing's 100%, that's small. That's teeny tiny. It's like 5%. Like, it's small. I could also use my chart way up here, so something above 2 standard deviations from the mean. If I'm using this chart above 2 standard deviations from the mean, that's this part right here. 0.235 and 0.15. It is 2.5%. That is the answer. 2.5%. It does look like it's about 0.25, or no, not 0.25, 0.025, or 2.5%. And then my favorite way to calculate it is, if the middle right here is 95, then I have a total of 5% in these 2 tails, which means I have 2.5% in each of the tails. So this tail is 2.5%, and this tail is 2.5%. The middle 95 is within 2 standard deviations of the mean, and then the 2 tails add up to 5%. That's 2.5%. We'll keep practicing it. Okay, about how tall are the tallest 0.15% of palm trees? By the way, I call this tail right here the small tail. There's the bigger tail, the small tail, and this little one, I call it the teeny tiny tail. So there's 3 tails. This question is asking about the teeny tiny tail. How tall are the tallest 0.15%? So the middle 99.7 means I've got a total of 0.3 in both tails. So I have 0.15% in both tails. This teeny tiny tail is 0.15%. I can see that up here in this chart too. This teeny tiny tail right here, whoa, major zoom, is 0.15%. How tall are the tallest 0.15% of palm trees? They are taller than 18, or 18 and up. 18 meters and up tall. About what percent are between 10 and 16 meters? About what percent are between 10 and 16 meters? Okay, I'm going to start by highlighting that. Between 10 and 16 meters. Between 10 and 16 meters. That's all of this space. Okay, I can do it a couple different ways. One way is to add up all of these areas. From here to here is 34%. From here to here is 34%. And this right here is, if you look at this one, 13.5%. I could add those up to get the answer. The answer is 81.5%. I could also, what I like even better than that would be to do, gosh, this is tough to explain. I would do this whole thing. Right here is 16%. So I would do 84%, and then I would subtract out this small tail right here, which is 0.25. That gives me 81.5%. We will keep practicing it. Okay? Let's keep practicing. This is the homework, but I'm going to do part of it with you. Let's see. I'm going to do the harder one, which is number 2. And I'll get you started on parts of number 3. Oh, number 4 for sure. You've got number 1. I've got number 2. Okay, here it goes. The EPA fuel economy estimates that for automobile models tested recently, the mean is 24.8 miles per gallon, and the standard deviation is 6.2. So I'm going to write that. It's normally distributed with a mean 24.8 and a standard deviation 6.2. Okay, I'm going to fill in my curve here. The mean is 24.8, and I'm going to go plus 6.2, plus 6.2, plus 6.2. And then I'm going to go minus 6.2, minus 6.2, minus 6.2. And that represents the distribution of my model. Okay. What score represents the 50th percentile? This is a symmetric distribution, so the mean and the median are roughly the same. So in this one, I would say 24.8, because the mean is approximately the median in a normal model. Okay, what interval would you expect the central 68% of all automobiles to be found? The central 68%. Remember, the rule is 68, 95, 99.7. The central 68 would be within 1 standard deviation of the mean. The central 68 would be within 1 standard deviation of the mean. So in this problem, it would be between 16.8 and 31 miles per gallon. I'm sorry, 18.6 and 31 miles per gallon. What interval would you expect it to be in? Let's make it more like an interval and say 16.8 to 31 miles per gallon. Okay, about what percent of autos should get more than 31 miles per gallon? About what percent of automobiles should get more than 31 miles per gallon? So I'm going to shade that in. That area right there that's in that lovely little lavender represents the more than 31 miles per gallon. So what percentage is that? I could look at my chart and it would tell me more than 1 standard deviation above the mean. That's all of this. That's 16%. These numbers keep reappearing everywhere. This right here is in fact, I'll do it in that one, 16%. And I knew that for several reasons. One is that if I've got the middle 68, then I have 32% total in the tails, 16% on this side, 16% on that side. So my upper tail has 16%. Describe the gas mileage of the worst 0.15% of cars. Describe the gas mileage of the worst 0.15% of cars. Okay, the worst. That means these are the gas guzzlers. These are the ones, nope, the other way around. Not these guys. This end. 0.15%, that tells me it's in the teeny tiny tail right there. The teeny tiny tail, which means they get gas mileage of 6.2 miles per gallon or less. 6.2 miles per gallon or less. Approximately what percent of cars should get between 31 and 37? Let's see. Between 31 and 37. Ooh. Well, I know between 31 and 37.2. And that chart up above is 13.5%. I know that for a couple reasons. One is I could look at the chart above. The other reason is from here to here is 16%. And I know this one from here on up is 2.5%. 16 minus 2.5 leaves me with 13.5%. Okay, you can try number 1. It's more straightforward than number 2. You can try number 2. As you're reading number 2, it's a normal model, mean and standard deviation. And you're gonna write right on the curve. I just want to talk about number 4 because it's a little tricky. So number 4, the distribution of heart disease rates per 100,000 people in 19 developed Western countries is close to a normal model. Normal model. From the normal model, the mean and the heart rate disease takes approximately what value? Okay, so my mean, right in the center. I would call that about, it looks like I went just below 200, so I would say it's about 190. So you don't, my point here with this problem is you're not just reading these numbers down here, you have to actually look at the curve. One standard deviation always goes out to what's called the inflection point. The inflection point is where the curve changes concavity. This is concave up right here, like a bowl, like it would hold water. This is concave down here, like water would run off of it. This right here is concave up, like it holds water. And then this point, these points are called inflection points. An inflection point is the point where it changes concavity. So the point is, that's where your standard deviation is going to be drawn. So that is one standard deviation away, meaning I went from 100 to 190. So that's about a standard deviation of about 90. And from about 190 up to 280, yep. Just an approximate. Normally distributed with a mean 190 and a standard deviation 90. The standard deviation of heart disease per 100,000 people. Oh, this one says, what's the mean? 190 death rate, ooh, per 100,000 people. And the standard deviation is 90. Okay. All right, see what you can do. Email me questions. We'll do a video conference later in the week.